course, the continuing. Good, good, good. All right, so welcome back to MAC1140 Pre-Calculus Section 009. Let's do the thing. Still working on that. Here we go. All right, you'll come back to that stuff in a little bit, but first we gotta do the normal hello. So this is MAC1140 section 009, which is pre-calculus. Today is the 2nd of September. So originally, and if you look on the syllabus, I had originally planned to cover two sections. Section 2.3, which is on getting information from the graph of a function, and also section 2.4, which is on average rates of change. However, what I found through the week is that my Monday, Wednesday classes, we didn't have enough time to really treat 2.4 the way it should. So your homework over the weekend this week is going to be smaller. We're just going to cover section 2.3. So that's getting information from the graph of a function. Which is section 2.3. That's what we're going to be doing today. So for example, I've shown you how to find domains, right? We've talked about the algebra processes for finding the domain of an expression or a function. You look for red flags and then you solve the appropriate equation or inequality. If your function is given to you graphically, meaning you're given a very nice graph of that function, but you're not given the algebra representation, then you can find your domain using just the graph. In addition to finding the domain, you can also find the range, which is cool because that's something we don't have a real easy way of doing algebraically. There are ways to do it, mind you, but not super easy ones. And in addition to domain and range, there's just a bunch of other shit that is so much easier to see using the graph of a function. So that's the game today. I think the place to begin is with domains and ranges though. So at the outset, let me just remind you the domain of a function is the set of all inputs and those are x values when we're looking on the graph, and the range is the set of all outputs which is the collection of y values when we're looking at the graph, right? So remember, inputs are on the horizontal axis, and usually we call those x values. They could be t or something else if we use a different variable. But the inputs are always the thing on the horizontal axis, and the outputs are always the thing on the vertical axis. And most of the time, those are, we call it y values. So when
what is the word before the colons? Input?
Inputs, yeah.
Before the colon.
Recall?
Recall. Oh, I'm sorry, I didn't hear you say that.
No, that's okay. My handwriting is not perfect. Yeah. So recall, the domain of a function is the set of all inputs or x values, and the range is the set of all outputs or y values. The way I like to describe this, especially when I'm working with younger people, is the smooshing game. If we're working on a slightly higher level, I would call it projection. What we're doing is we're going to project the graph. But I'll show you what I'm talking about. I think that will be sufficient. My wife and I are both a little bit sick, and I'm feeling some of those body aches and weird fatigue today. So I apologize if my art is worse than normal. And so I'm going to say we've got a thing over here like this. It's going to come down to the origin here. And go up in a symmetric fashion. Go up a little higher. this. And then a little gap. Let's do it like this. Gap. A little constant segment there like that. Maybe open on this end. So let me flag this as like 2, 4, and 5. And here it's -2, +2, 4, 10. Okay, so finding domain and range graphically. I'll get my hand out of the way in a second. I call it the smooshing game. I'll just give you a second to get this down. I'll call this function over here f of x. Call the horizontal axis here the x-axis. Right. All right. So what is the smooshing game? It's what it sounds like. Pretend like I have a thick Russian accent and this is the hydraulic press channel. Here comes my press. I'm going to smoosh this whole thing down onto the x-axis. So to find the domain, you smoosh the graph onto the x-axis. All right, let's see what happens if I smoosh this onto the x-axis. So again, think of a big hydraulic press coming down and just pushes everything down onto the x-axis. This point right here is going to get pushed down onto -2. So -2 gets hit. This little curvy segment in here is going to get pushed down onto this portion of the x-axis. This curvy segment over here is going to get pushed down onto this stuff. And remember what the open circle means. It means that there isn't actually a point there, right? This pattern continues up here, but then there's not actually a point there. So there isn't anything to come down and smoosh onto the 2. So from this piece, I would have the closed interval on the left from -2 up to open on the right, +2. That's just from that piece. If I continue doing that, if I smoosh this guy down, this filled in point right here is going to come down and smack the 4 on the x-axis. And this whole segment in here is going to come down and hit everything in here. And then just like the other guy, there isn't actually a point on the graph at that filled in circle. So the 10 doesn't get hit, but everything up to it does. Okay, and the 4 did get hit, so I'm going to use a bracket on it. The shaded region on the x-axis is the domain. Another way to think of this, the actual technical term for the smooshing game is projection. Mathematics, we like to project. That is what it sounds like. You imagine there's a very bright light shining down from up here. Then all of these would be projected onto these intervals, or it's like a shadow, right? If there's a very bright light shining down from above, the shaded purple intervals here would be the shadow of the graph. So that's another way to think of it. smooshing or projection or shadows. So if I want to write that out, the domain here is the left closed, right open interval from -2 to 2, union with the left closed, right open interval from 4 to 10. Questions about where this domain is coming from or how we found it? She just took the coffee. Yeah. All right. To find the range, we do the same thing, but we smoosh from the side. All right. So now my hydraulic press is coming in like this. And smooshing everything onto the y-axis. So this point right here, if I smoosh this segment onto the y-axis, is going to be projected over to the 2. And this whole little curvy segment would be projected onto this interval of y values. So that's just coming from this piece right here. And there is a point on the graph at the origin there, so I'm going to draw it here. It might be a little hard to see. We would start down there. This portion of the graph right here is going to project onto that same stuff. That stuff gets hit multiple times. That's okay. And it continues a little further up here. So this portion is going to get projected over this way, all the way up to, and then there's an open circle here. So the 4 doesn't actually get hit. So if you just look at the first piece of the graph, its range would be this, which is the interval from 0 to 4. Right? Y equals 0 is right here. Everything between 0 and 4 gets hit. 4 itself does not get hit. This whole segment over here, again, imagine it's rigid, and I'm going to come in with my hydraulic press and just go and push that whole thing over. It all piles up on the 5. That's the only y value that gets hit by that. So my range would be from 0 to 4, left closed, right open. Union with, this is not an interval, right? This is just the single number 5. So we write that as the set containing, just the single element 5, like this. In other words, to find the range, you smoosh the graph onto the y-axis. So I think this is kind of neat that you can have a whole portion of the graph here that corresponds to an interval in the domain correspond to just a single number in the range. But that makes sense. This is a constant, right?
If it's a single number, you just put curly brackets every time?
Right. Yeah. Remember, the curly brackets are how we denote a set. So
Okay.
have a set just containing 1 or 2 or 3 things, then putting it in curly brackets and listing those things is nice. If you have a set containing infinitely many things like this, I can't list them all. So that's why we have the interval notation.
How do you know whether it's included or not? I guess it's both included and not included. Yeah, that's interesting. Okay.
I like that question. Let's hold on to that for just 1 second. I'll be right Sorry about that, guys. My son is, we're all a little bit sick in the house, and my infant son needed some Tylenol. So I want to measure that up for him. All right. Gavin had an interesting question about the singleton here, and I just want to clarify what it was you were thinking about before I ramble about it. So could you just reiterate that question for me?
I'm just confused because you're kind of condensing a point that is included, like on the X, it's included, 4 is included, whereas 10 is not. And
Right.
that's, I don't know, I guess that doesn't affect the Y values though. Could be a dumb question.
No, not a dumb question at all. So let's think of it like this. If I list some points that are up here explicitly, like this filled in one here is 4, 5. Right here, I might have 4.8, 5. Over here, I might have like 9.9, 5. Remember the definition of the range. The range is the set of all the Y values or outputs that are on the graph. So this whole line segment contributes only a single value to the range, because even though there's like infinitely many points here, they all have the same Y value. They all have Y value 5. And it's true that this guy right at the very end here, this open point, which would be, if it were filled in, would be 10, 5, doesn't actually contribute anything to the range. But if he was filled in, he would be contributing redundantly to the range. He would be just another point on the graph whose Y value is 5. So this guy doesn't actually contribute to this set, but all the other things just to the left of him over to here do contribute to that range. But they all contribute the same thing. They're just like 5s piling up on top of each other. If this line had some slope to it, like maybe it came down like this or up like this, then this would be the only spot on the graph where the Y value appears to be 5. And because it is open, 5 would end up not being included in the range. So that, for example, if you had something like this here, then all of these other points would have Y values that are beneath 5, and 5 would end up not getting hit. So it is a little bit funny, but I think if you're ever uncertain about what's going on, so you play the smooshing game. Smooshing game, I promise, works great. If you end up a little uncertain after you do that, after you kind of shade the region over here, you can always come back to the definition and ask yourself, okay, well, does this make sense? It might be a little counterintuitive. And often in mathematics, our intuition is powerful and useful, but we are dumb animals at best. So our intuitions cannot always be trusted. Often we need to kind of slow down and check our intuition. So it might seem weird. Yeah, infinitely many points, just giving me one value. Another way to think of that is if you were to union all of these Y values, you have infinitely many, but they all have the same Y value. A union of infinitely many sets, all containing the single element 5, is still just the single element set 5. So it's funny, and it certainly is counterintuitive. And that's why we have the smooshing game, because it kind of helps with our animal intuition's deficiency here. Is there anything else we'd like to talk about with regard to this example or this technique? You guys remember the Dirichlet function from last time? That was a weird guy too. Even though he doesn't have any connected portions of that graph, it's all just a bunch of dust sprinkled along Y equals 1 and dust sprinkled along Y equals 0. His range would be the 2 element set 0 and 1. And his domain would be all real numbers, but it's broken up in a very strange way. So you have plenty of opportunity to practice this in the homework. And if you do get stuck on anything, remember you can always ask in the Discord. You can send me a Canvas message or come by one of the office hours. Domains and ranges are great. But there's lots and lots of other stuff we can do with graphs somewhat easily, especially if the graphs are of good quality. In particular, they're a nice way to compare outputs. Before I move on, let me just share with you a little piece of vocabulary. in math, especially calculus, if we ask, where is something? Specifically a feature on a graph, that always means for what x value or for what input. And well, let me just leave it at that, actually. I'll just leave it at that. So the definition of a function is the way it is for precisely this reason. We talked about what functions are in our last class. We said functions are rules for pairing inputs and outputs, but subject to this constraint that every input goes to one and only one output. The reason for that definition is to allow for this understanding. And I'll come back to this in a little bit. But because, for example, if you were to try and tell me that you want to tell me what's going on at this point right here, you could say that's the point where y is equal to 2, which is not a false statement, but it doesn't uniquely identify this point. If you tell me this is the point where x is equal to -2, there's only one point on the graph whose x value is -2, but there's 2 points on the graph whose y value is +2. So if you tell me this is the point where y is equal to 2, I don't know if you're talking about this point here or this point here. It could be either. So if you're trying to point out the location of something on the graph of a function, in other words, you're trying to tell me where something is on the graph of a function, you always want to tell me the x value. Similarly, up here, if you want to describe this filled in point, you could tell me it's the point where x is equal to 4. And immediately I know what you're talking about because there's only one point where x is equal to 4 because the input 4 is only allowed to be sent to one output. That means there can't be any other point above or below x equals 4. But if you tell me it's the point on the graph where y is equal to 5, you could be talking about any of these points, right? And there's infinitely many of them here. So the definition of a function is the way it is, precisely so we can do this, precisely so we can say, okay, where is this hill or where is this valley in the graph? Oh, it's at x equals 3. And there's only one point on that graph where x is equal to 3 because the graph is a graph of a function. So if I ask you, where is something? Where is the min? Where is the max? Where are we increasing? Where are we decreasing? Any of that, where always corresponds to x values. With that in mind, let's see if we can figure out where functions are increasing and decreasing. I'm going to give you a kind of intuitive definition, and then I'm going to give you a technical definition, and there's going to be a bit of subtlety. But let's start with the intuitive stuff. All right. Let's say we've got something like this. And the arrows kind of indicate that the graph continues going in that manner. So it keeps going this way over here, and it keeps going down like this over here, forever and ever on that. Imagine a little fella whose whole world is the graph of this function. And he's walking from left to right along this graph. He always walks from left to right. It's a tick, whatever. He can't help it. Always going to the right. If he's going downhill, then the function is decreasing there. And if he's going uphill, then the function is increasing there. So like right here, he's definitely going downhill. I would want to say that this function is decreasing everywhere over here, because if he's going left to right, he's going downhill. Over here, he's definitely going uphill, and everywhere along the highlighted portion of the graph, I would want to say he's increasing. All right, the function is increasing because everywhere along this highlighted portion, he would be going uphill. And everywhere over here, he's going downhill. So this is all decreasing. So we can chop our input space up into a few different regions. I'll call this A. I'll call this B. So if, and this is going left to right, we go uphill, that means increasing. And if we go downhill, that means the function is decreasing. And you always want to give this information as open intervals of x values, right? Because I'm asking, where is the function increasing? Where is the function decreasing? That word where always translates to for what x values. The reason for open intervals is a little bit more subtle. Let me first just write down the result for this guy. So here, f is decreasing. And the language we use is decreasing on this interval or increasing on this interval. Here, f is decreasing on, well, everywhere to the left of A, right? This is all downhill, downhill, downhill. So decreasing everywhere over here and everywhere over here. So that's from negative infinity up to A, union with B to infinity. And f is increasing on the open interval A to B. And the note intervals of increase and decrease are always open intervals of x values. And I want to emphasize the x values part. So we talked about why x values, right? Because if you tell me an x value, there's only one possible point on the graph with that x value. But if you tell me a y value, there could be many points on the graph, right? This y value corresponds to this point over here, this point over here, and this point over here. I don't know which one you're talking about. Maybe this is y equals 1. If you're to tell me that this function is decreasing when y is equal to 1, if you're talking about this point, then you're right. If you're talking about this point, then you're wrong. If you're talking about this point, then you're right. All three of those points have y equals 1. But if you tell me the x value, oh yeah, I know you're talking about this point. There's only ever one point on the graph, a particular x value. Why open intervals? So intervals of x values, that makes sense because that uniquely identifies a portion of the graph to specify an x value. But why open intervals? Well, let's think about what's happening right here at this point. At this point, which is a comma f of a, I'm not going downhill anymore, right? I'm walking downhill, 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 downhill. And everywhere over here is uphill, 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 uphill. But right there at that moment, if you stop me at the bottom of that valley and ask me, hey, right now, are you going up or down? My answer is, I'm not doing either of those things. I am briefly, just for this one moment, chilling with respect to my height. I was going downhill. I'm about to be going uphill, but right now I'm not doing either. So it would be wrong to say A is a part of the interval of decrease, but it would also be wrong to say A is a part of the interval of increase. So we always use open intervals because at the end points where you're transitioning, you're neither going uphill nor downhill. There is another answer to that question, which is slightly more technical. In calculus, one of the ways to discover where a function is increasing and decreasing is to find a related function, another function called the derivative, and then to figure out where that function is strictly greater than 0 or strictly less than 0. And you've seen that when you solve strict inequalities, you always get open intervals. Well, that's why. That's why you get open intervals for increasing and decreasing, because that related inequality is a strict inequality. And we'll see that about halfway through Calc 1 next semester. We do need the technical definition here, though, so let me share that with you. The function f is increasing on the interval, I'll just use the letter I, means for any x1 or x2 that are elements of the interval I with x1 smaller than x2, we have f of x1 is smaller than f of x2. So what does this mean anyway? Well, look at this function right here, right? We said that this function is increasing on the open interval AB. So if I take x1 to be over here and x2 to be over here, then the y value here is f of x1 and the y value here is f of x2. Well, is f of x1 smaller than f of x2? Yes, it is, right? Because this point has a y value that is smaller than the y value at this point. So this is just the technical way of saying the same thing, right? As you walk from left to right, as you look at bigger x values, the y values should get bigger as well. And then if you flip the inequality, the second inequality over, you get the definition of decreasing. So we say the function f is decreasing on the interval I means for any x1 and x2 in the interval I with x1 smaller than x2, we have f of x1 is bigger than f of x2. So if you look at two inputs, one larger than the other, the y value at the first input should be bigger than the y value at the second input. In other words, as you go left to right, the y values get smaller and smaller. And that means you're going downhill. So technical definitions like these are not necessarily great for building intuition, but they are really good at solving kind of subtle or challenging problems. They're also a good source of like true-false questions. So make sure you acquaint yourself with the inequalities associated with increasing and decreasing. We're going to come back to this and look at some more fun increasing, decreasing problems. But before we do that, I want to talk a bit more about inequalities and how they can be understood in terms of graphs. While we're there, we're also going to talk about some equations that can be understood in terms of graphs. Let's do it. So I don't remember if it was this class or one of my other 1140s this semester, but when we were looking at some inequalities on, I think the first day, somebody was like, can we do this graphically? Is there a way to do this using pictures? And I said, yes, but we're going to do that later. Well, now is that later? So this is solving equations and inequalities graphically. All right, I'm going to draw a kind of just generic picture here. Some color. So my x-axis, this will be my y-axis. And then in blue here, I'm going to draw a function which I'll call g of x. And in purple, it's another curve function, we'll call that f of x. Extend this out a little bit. Okay. And then the 2 points here where they touch, call this one A, I'll call this one B. So the solution, and these don't need to be at the same height. They look like they're kind of close, but you know, this one's a little bit lower than this one. The solution to the equation f of x equals g of x. Well, equations of this form, like, you know, x squared equals 5 minus x, those are x values, right? You get some numbers out like x equals 1, x equals 3. Graphically, the solution to those equations are the x values where the graphs touch. I'm asking for what x is f of x equal to g of x. In other words, where along my input space do I have outputs that are the same height? So right here at this point, f of a, well, that's the y value on the purple graph, and g of a, that's the y value on the blue graph, they're the same. So f of a is equal to g of a. In other words, x equals a is a solution to this equation. And by precisely that same logic, if you look at this point right here, along the purple graph, this is the point b comma f of b. And along the blue graph, this is the point b comma g of b. They both have the same x value, of course, but the fact that they have the same y value is the big deal. Those graphs touch there. And that means that f of b is equal to g of b. So let me annotate a little bit. This point on the one hand can be thought of as b comma f of b. And on the other hand can be thought of as b comma g of b. It's a point that's on both graphs. Well, the fact that those points sit right on top of each other means f of b and g of b are equal to each other. And if f of b is equal to g of b, that means x equals b is a solution to the equation f of x equals g of x. And the same shit's going on over here. I won't relabel it. So the solution, in this case, solutions to the equation f of x equals g of x are x equals a and x equals b. And these come as x values where the graphs touch, intersect. The solution to the inequality say f of x is less than g of x, this is going to be all the x values where f has a smaller output than g. And remember the outputs, those are the y values on the graph. So this is going to be all the x values where the purple graph is underneath the blue graph. So the solution to that inequality is the set of all x values where the graph of f is beneath the graph of g. So you can kind of look one x value at a time or just take a few samples. Like if I look at this particular x value right here, the purple graph at that x value is beneath the blue graph at that x value. So this guy, whatever he is, would be a part of the solution set to this. If you were to look over here, the purple graph is above the blue graph, right? The blue is beneath the purple is above the blue at this x value. So this would not be a part of that solution. So for this particular example, we would have the open interval put it over here. From A to B. Right, it's precisely these x values in here between A and B where the purple is beneath the blue. If I look over here, the purple is above the blue. If I look over here, the purple is above the blue. But between A and B, between this x value and this x value, everywhere in here, the purple is beneath the blue. And you can probably guess what's coming. Solution to f of x is greater than g of x is the set of all x values where the graph of f is above the graph of g. In this case, that would be everything to the left of A and everything to the right of B. That's negative infinity up to A, union with B to positive infinity. And if you changed this to a greater than or equal to, you would use brackets on the A and the B. So we'll look at a specific example. We're going to get a trio, an equation, and two inequalities. We're going to solve those graphically. The catch is I haven't really taught you guys how to graph much yet. Right? I can assume some stuff from your past, but really we try not to bring a lot of assumptions in. So all the problems that you're going to encounter like this in your homework, the graphs will be given to you. Any questions on what we're saying here? Okay, then let's do this. Let's put this into practice. We're going to solve 2x squared plus 3 equals 5x plus 6. 2x squared plus 3 is greater than 5x plus 6. And 2x squared plus 3 is less than or equal to 5x plus 6. And we're going to do all of this graphically. Now, I'm hoping that everybody remembers how to graph y equals 5x plus 6. And although it might be a little too optimistic, I would also hope that you remember how to graph 2x squared plus 3. But I'm going to give you both graphs here. I'll do one of them in blue and the other one in purple. Two x squared plus 3 looks something like this. It is a parabola opening up with its vertex at 0, 3. It's been stretched vertically compared to x squared by a factor of 2. So this is f of x equals 2x squared plus 3. I'll label some points in a second. The other function in play here is 5x plus 6. That's a line. Its y-intercept is 6. It has a slope of 5. My vertical axis here, I'm scaling quite a bit. That line looks something like this. Should be a straight line. Sorry. Okay, so this is, I'll call it g of x. 5x plus 6. So if you're told to do something like this, first thing you got to do is give each side a name. Call the left-hand side f of x, call the right-hand side g of x, or vice versa. It doesn't matter. Then you graph both functions. Of paramount importance are these intersection points, specifically their x values. This one happens to be -1/2, and this one happens to be 3. And unless you can get that information straight from the graph, this method is not particularly useful. Because normally you'd have to solve an algebra problem just to find those intersection points. And at that point, you might as well just solve these equations and inequalities algebraically. But if you're given this, as you have been here, you can then solve each of these really nice and quick without doing too much work. So let's start with the equation. 2x squared plus 3 is equal to 5x plus 6 has solutions. What? What are the solutions to that equation based on this graph?
X equals -1/2 and x equals 3.
Very good. All right, it's the x values where the two graphs touch. All right, what about that first inequality? 2x squared plus 3 is greater than 5x plus 6. This is an inequality, so the solution is most likely a set, some intervals, something like that. Kind of in words, what am I looking for here?
When all of the x values for 2x squared plus 3 are greater than 5x plus 6.
Good. Yeah, exactly. So I'm looking for the x values where 2x squared plus 3, which is the blue graph, is greater than or lies above the purple graph. All right. What are those? Where is the blue graph above the purple graph?
Negative infinity to -1/2, and then union 3 to infinity.
Very good. Very good, right? If you take any x value from over here, like this guy, the purple graph at that x value is beneath the blue graph at that x value. And same is true over here. You take any x value over here, the purple graph at that x value is beneath the blue graph at that x value. So this would be negative infinity to -1/2 union with 3 to positive infinity. And then the last guy, the solution set to the last inequality, 2x squared plus 3 is less than or equal to 5x plus 6. That's anywhere that the blue graph is beneath the purple graph. So if you look at this guy, for example, right here at this x value, the blue is beneath the purple. And that's true for any x value between -1/2 and 3. So the interval here has endpoints -1/2 and 3. What kind of delimiters should I use? Brackets or parens?
Bracket.
Yeah, we want to use brackets here because at x equals -1/2, those two functions are equal to one another, right? We have said that explicitly over here. So certainly it's true that they are less than or equal to, right? So these will both be brackets. Any questions on this one? Okay. The last thing I want to kind of show you today are what people call extrema, extreme values, mins and maxes, specifically local extrema, which are sometimes also called relative. And we're going to connect that to the increasing decreasing business, at least in the case where the graph is nice and smooth. So, local extrema. And extrema is just the word for min or max. So mins, maxes. Besides local extrema, there are also things called absolute or global extrema. those are important, but we're not going to discuss them right now. Right now, we're just worrying about the local version. Okay, definition. The function f has a local min at x equals a means that the y value or the output from that function at x equals a should be smaller than any of the y values or outputs nearby. In other words, f of a should be less than f of x for any x values close to a. And that word close is has a bit of a fudge factor behind it. What does it mean to say two numbers are close to each other? It's not very quantitative. But I'll show you precisely what is meant by that. And we say the function f has a local max at x equals a. You just turn the inequality over. That means f of a should be bigger than f of x for any x values close to a. So I'll draw a separate picture for each of these and try to convince you that the inequalities are reasonable and what they should be. Before I do that though, I've got one little caveat. The author of your textbook, James Stewart, who is normally a reasonable and intelligent human being, does something fucking dumb here. No nice way to say it. He uses weak inequalities for these definitions. And that's just wrong. Now I have to show it to you because that's what's in your textbook. But rest assured, any mathematician in the world would look at this and say, what? That doesn't make sense. And I'll explain why in a second. But in your notes, I recommend using the strong inequality, or at very least making a note that this really should be a strictly less than. This really should be a strictly greater than, even though it's not like that in the book. All right, so. Put a right here. And maybe your function looks like this. There's your x-axis. This point right here is a local max. Because if you look nearby, so take some open interval centered at A, and you take any x value from that interval, I would say that this x is pretty close to A. Then the y value on the graph there is smaller than the y value on the graph here. Yeah? And this will be x comma f of x. And up here is a comma f of a. And f of a is this y value. F of x is this y value. And I think you'd agree that if I picked any other x from the purple interval below, that f of that x would end up beneath f of a, because all the other parts of the graph here are lower down than this point right here. That's what's meant by a local max, and that's precisely what this inequality is describing. This inequality is describing. F of a, this y value, the y value at this point, is bigger than any of the y values nearby. So this is a local max. And the picture for a local min is very similar. You take a little open interval centered at A, and you take an X value from anywhere in that little interval. You're going to end up with a larger Y value than you have right here. And you compare those Y values. Here's f of A. Here's f of X. So the same thing's going on, it's just flipped over, right? Where the Y value at this point is the lowest Y value when compared to any of the nearby Y values. So that's what we would call a local min. In practice, how do we find these? Well, what you do is you look at the graph. If you think you found an interesting point, a min or a max, you should imagine a little window around that portion of the graph. If your point is the tallest point anywhere in that window, then you've found a max. And if that point is the lowest point anywhere in that window, then you've found a min. Okay, so let's look at a nice simple example. And we're also going to state the intervals of increase and decrease. As it turns out, these things are actually connected if your graph is nice and smooth. So this example will be gentle. I'll also share with you some vocabulary here. Okay. So do we see any extrema, any mins or maxes? Yeah, Suzanne?
Would it be 5 being the maximum because it's at the top of the graph?
Yeah, if I draw a little window around this portion of the graph, that point right there is the tallest point anywhere in this window. So this is a local max. And over here at 1, if I draw a little window around this portion of the graph, that's the lowest point anywhere in that window. So that's a local min. And the vocabulary here, we would say, if I ask you where is the max, that's what's the X value. Remember, where always means for what input. So I'd say F has a local min at X equals 1. And the min value, so if I ask you what is the min or what's the min value, that's the Y value, which is 1. So here's the first part of our answer. F has a local min at X equals 1. Where is the min? That's the X value. What is the min? That's the Y value. So the way I would describe the max here is I would say F has a local max at X equals 5. And the max value is, well, it's the Y value at this point, it's 4. So the max value there is 4. So if somebody asks you, what is the max? What is the min? They're asking for the Y value. And if they ask you, where is the max or where is the min? They're asking for the X value. All right, the other thing I want to talk about with this example is the intervals of increase and decrease. So who can help me out with that? F is increasing on what interval?
On 1 to 5.
Good, the open interval from 1 to 5. Right, this is not an ordered pair. I think we talked about this a little bit last week. It's possible to confuse yourself here and say from the ordered pair 1, 1 to the ordered pair 5, 4. That's not how we do it. You always give me open intervals of X values. So please be careful. All right, this is an open interval. So we're saying right here, the function is increasing. So if there's one kind of meta lesson to take home from today, it's that when you're telling me where something is, always X values. Okay, where is F decreasing?
Negative infinity to 1 united with 5 to infinity.
Perfect. Everywhere to the left of 1, which is negative infinity to 1, union with everywhere to the right of 5, 5 to infinity. Okay, what do you notice about the mins and maxes? So we're decreasing here, increasing here, and decreasing here. What's the relationship between the decreasing, increasing, and the extreme line?
The extremas are the points that aren't included in the increasing and decreasing.
Yeah, in particular, the mins will show up where you go from decreasing to increasing. If I'm going downhill, 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 and then uphill, 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 that means I had to roll through the bottom of a valley, which is going to be a local min. And if I'm going from uphill, uphill, uphill to downhill, 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 that means I went over the top of a little mountain, which has to be a local max. So where you go from increasing to decreasing, you'll have maxes. And where you go from decreasing to increasing, you'll have mins. This is only true for functions where the graph is smooth and connected. If the graph is not connected or not smooth, then this is not true. But most of the graphs we look at will be smooth and connected. So it's a nice thing to observe, and this is a big deal in calculus. I'm not going to write it down, but just food for thought. If you go from decreasing to increasing, you might have a min there. If you go from increasing to decreasing, you might have a max there.
So can you have multiple local minimums and maximums on one graph with like
Absolutely.
multiple curves? Okay.
Yes, yes, we certainly can. So let's take a look at something a little bit more complicated. All right, so this time we're just going to find the local extrema. And I'll make this one nice and weird. Let's do something like this, and then right. Like that. Let me get some numbers in here. So I'll call this -1. Here's 1, here's 2. And y values. Let's see. Okay, I meant for those to be at the same y value, but all this +1. Is 1.5. All this right down here, 0.5. What else can we, we'll call this up here, +2. Okay. So I'd like to find the location and min or max value at any of the extrema here. And let me, let's also say this continues off like that. Okay, so here the graph is neither smooth nor connected. This is a much weirder function. But the guiding principle is still the same. Identify any points where you think there's something interesting going on, then draw a little window around the graph and try to tell whether that point that you think is interesting is the tallest point in that window or the shortest point in that window or neither. So what do we see as far as, let's look for mins first. Does anybody see a local min?
2.
See over here, this kind of looks like some min behavior. But remember, the value of the function at 2 isn't specified by the open hole. The open hole doesn't have a point there. It's actually up here. So while there is something going on at 2, it's not a min. All right, if I draw a little window around the graph there, the actual point at 2 is up here, and this is not the lowest point anywhere in that window, right? Because there's stuff down here. If this were filled in, then that would be a local min.
I'd say 0, 0 would be a good spot.
Yeah, this one's a little bit non-obvious, but the graph goes through 0, 0 right here. So there's a local min at x equals 0. And the min value, the y value there is 0. Are there any other local mins here? Oh, I need to Sorry, I haven't told you what this is. Let's call this over here 3.
-1.
Very good. -1 is also a local min. So there's definitely something weird going on here. So let's put our little window there. All right. Here's my little window. This is the point on the graph at x equals -1, right? Not up there. There's nothing here. There's a hole there. The actual point on the graph is right here. And this most definitely is the lowest point anywhere in this little window, right? There is no point on the graph which is beneath this in that window. So that's got to be a local min. So at x equals -1, we have a local min. And the min value is what? Anybody help us out? Jalen correctly identified as the other local min, but what's the min value?
Is it 1? Is
It-
it like absolute value or no?
So remember, min value, the value there, I should say it like this, is always the output from the function at that point, right? So here the output was 0, the y value is 0. So where is the min? That's always the x value. What is the min is always the y value. So the output at -1, that's f of -1. What is f of -1?
0.
0, right? Here's the point that's actually on the graph. So it's tempting to say that this guy has something to do with that, but he really doesn't. Really does not. That's it for local mins. There are no other local mins here. So what about local maxes? This kind of looks like a local max, right? At least this does. But that point that would be the local max is missing. So there's no max here. Also, we can't have a point being both a min and a max. That doesn't make sense. What's going on right here? If I put a little window around the graph where x is equal to 2, that looks like this. And the actual point on the graph at x equals 2 is this filled in point right here. Is this the tallest point in that window?
Yeah.
Yeah, he absolutely is. So this is a local max. So there's a local max at x equals 2. And the max value is, well, whatever it is, it's definitely f of 2, right? It's the output when we feed the input 2. And that looks like it's 1.5. Okay. So even though this certainly doesn't look like the top of a hill, it's still a local max. And the game or the thing that will help you identify those 100% for sure is this window thing, right? So just put a little window around it. You can draw them in. There's no harm in that. Put a little window around the graph there. And ask yourself, is that the tallest point in the window? Yeah, it is. Okay, so that's a local max. Are there any other local maxes?
No?
3.
Yeah, over here at 3, right? If I put a little window around this point, around the graph where x is equal to 3, that filled in point right up here is the tallest point in that window. So that's a local max. And then not coming from this, coming from this. So the y value up there is 2. All right. So these are mins and maxes. And if your graph is nice and smooth and connected, easy peasy. But if your graph is wonky and weird, piecewise, holes, gaps, jumps, shit like that, then it can be a lot less obvious. Notice that the increasing to decreasing argument really doesn't work for this. Doesn't work at all. Here I'm increasing, 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 and increasing, increasing, increasing. So I didn't change from increasing to decreasing, but I still had a max. Or over here, I go increasing, 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 decreasing, decreasing, decreasing. But somehow that's not a max, that's a min. So that idea of increasing to decreasing gives maxes and decreasing to increasing gives mins only works if the graph is smooth and connected. You need both of those things. In calculus, we'll call those differentiable, right? Continuous and differentiable correspond to connected and smooth respectively. But only under those conditions can you say things are that easy. Otherwise, you need to be careful. And the way of being careful here is the little window argument. Okay, questions for me on this? Alrighty, that's good because I think we've gone a little bit over time. So I'm going to go ahead and end the meeting here for today. Starting next week, we're going to talk about average rates of change, and then we will kind of push forwards into the study of specific families of functions. So this average rate of change, I wanted to do this week, but we really don't have time. We're going to talk about transformations and means of combining functions. But that is it. Please work hard on that homework set that is up. And I will see you guys on Tuesday of next week.
Thank you, sir. Have a great day.
Yeah, you too.
Thank you.